These are really important classes, and some people are missing. I don't know. So maybe they are listening to videos. So yesterday we looked into the problem with gradient descent algorithm. We understood gradient descent algorithm is learning the theta. It starts with a random theta, and then it learns. It actually learns. Right? This is called as learning. Okay. I'm actually highlighting this is called as a learning because in deep learning we'll have a concept called as transfer learning. If you understand how exactly this theta is learning, the transfer learning is a very simple concept. What is happening here? With each iteration, the existing theta is being modified and you are learning a new theta. You're getting a new theta. Right? Like that, in deep learning, if you have a model which is already trained on maybe 1,000 images, 1,000 different classes of images, maybe uh, maybe 200,000, maybe 3 lakh, 4 lakh images you have belonging to 1,000 different classes. The model is trained, and now your friend needs to build a model, and he has got only 10 images of maybe two classes, maybe 100 images of two classes. He or she can take your model and start learning from where you have left with this. So the theta is, and next iteration is learning from there, right? Next iteration is learning from there. Next iteration is learning from there. Like that, you trained a model on 300 images, 300,000 images of 1,000 different classes, and your friend took your model and learning from there. That actually makes the model better with less data. Generally, deep learning needs huge volumes of data. If you have less data, then you go with machine learning. If you have huge data, you should definitely go with deep learning. You know, why deep learning? Why machine learning? Why are we learning machine learning also? Machine learning algorithms also, because when data is less, you don't have other way, right? You need to go with machine learning algorithms only. So you need to remember that. Okay. So transfer learning, this gradient descent learning is what is transfer learning basically. I'll talk about this transfer learning there again in deep learning, but for simple understanding, I spoke about it here. You got any questions on the statements I made? Does it make sense? Yes, no?
Rama.
So, the algorithm is working like this. Okay, how is it actually learning? We don't have gradient descent algorithms implementation in scikit-learn. We have implementation for stochastic gradient descent, because gradient descent algorithm uses whole data in each iteration. How is it using whole data in each iteration? This is how it is. So the algorithm is learning step by step. I'm actually switching back and forth between screens. You can see the convergence and divergence screen, I think. Yes.
Yeah, now we are in that screen.
Yeah. So in here, the algorithm is learning slowly, step by step by step by step, right? So with each step, right? With each step, to make a step, just to move from here to here, it used whole data. How is it used? This is how it is, right? So I have taken 70 iterations. You can take n number of iterations. We may have to take more number of iterations when the parabolic curve is not steep enough. This parabolic curve in the convergence and divergence diagram, If it is not too steep, right, it is slant. Right? It is slant like that. It's slant like that, right? Slant means, like a plate, right? Instead of a bowl, if it is like a plate, then it takes more iterations to reach global minima, and sometimes it may fail to reach global minima because when once the algorithm reaches the bottom of the pit, right, the slope becomes almost zero. When slope becomes almost zero, the calculation, right, this whole calculation becomes kind of zero, and next theta, stays the same place. That's our goal also. We want to reach to a place where the slope is zero, slope of the tangent is zero, right? So this is how it is using. So it is taking the whole data and doing the vectorized multiplication. Okay, it is calculating the predicted value theta x, x dot theta is the predicted value, or you can say theta transpose x also. It depends on the way you took the x, right? If you took x, each row as a vector, then you need to do theta transpose x. If you took x as x, right, whatever each row as row, then you can actually, calculate the predicted values here and then minus your, actual value, that is the error, or you shouldn't be saying error here, and then multiplying with x. How did we got this? You remember, right? How did we got this? You remember. This is gradient, I said, and yesterday I calculated and showed you. Do you remember that? Do I need to show that again?
We remember it.
Yeah, good. Right? So this is gradient. Gradient is nothing but slope of the tangent at that given theta. How do you find out at that given theta? You substitute theta into it. You find out the equation, keep that aside, slope equation, gradient equation, you find it, keep that aside, and with each iteration you substitute your new theta, right? Theta is equal to theta minus eta into gradient, that is a new theta. You come back, you substitute that, right? At that theta you are calculating gradient and you are finding new theta, like that. In each iteration it is using whole data. That is the problem with gradient descent. Suppose that if you have million records, if you try to do this looping, it will come, it will become, it will be out of memory error. It will throw out of memory error. Maybe by second iteration, third iteration, it will throw out of memory error because memory will not get cleaned up that fast. I forgot that name in Java. Garbage collector, right? In Java, there is a concept called as garbage collector. Unused variables will be cleaned up ad hocly. There is no systematic way. As soon as you release the variable, the compiler will not clean it. Like that in Python also, it will not be right away. So you will have some matrix manipulations already residing in memory, and they'll occupy lots of memory, and you'll get out of memory error. That is the biggest drawback with gradient descent. In fact, we had this issue in normal equation also. We came to gradient descent to solve that problem, but we still having the problem. To avoid this problem, we are going into stochastic gradient descent. Instead of taking whole data, right, here we took x, and y. That means if you have 1 million records in x, whole 1 million records you will take, right? All x's, 10,000 columns and 1 million rows you take and calculate the gradient. But in stochastic gradient descent, we will not take the whole data. If you see this, if you focus on the second for loop, there are two for loops here. Okay. If you focus on the second for loop, you can see the screen, right?
You see only for one.
Not yet. Not yet.
Stochastic gradient descent screen. Do you see?
Yes. No.
Now it is.
Now it came.
Google Hangouts, right, is getting fast compared to Microsoft Teams. Okay, that's fine. So if you focus on the second for loop, no, forget about the first for loop. I'll talk about the first one. But if you focus on the second for loop, for I in range of m, what is m? Number of records in the data set. If you see a little top, right, fifth statement in these lines, m is equal to x dot shape of 0, right? If x is a data frame, shape will give you a tuple, right? Rows and columns. I am taking the rows. 0 is the rows. So m is the number of rows there, right? So for I in range of m, y predict is equal to x dot theta. What is the theta initially? What is the theta?
25.
25.
25. It's a random number. I too don't know whether it is close to the original, global minimal, best fit lines theta or not. I've taken some random number. Y predict is equal to x dot theta. What did it do? Did it predict did it do predictions for whole data or only one record? Y predict. Y predict. Will it have all records predictions or only one record?
All records.
All records, right?
Yes. Yes.
So here we predicted all records. If you look at the green box, right, there I am randomly choosing one number. No, np.random.randint of m will give me one integer in the range of m numbers, 0 to m. It will give me one number. Okay, and then I am saying xi and yi. I am choosing one record, ith record. What is the index? The I is the index, right? What is that index? The random index, whatever I chose in the top. Suppose that you have 1000 records and you said np.random.randint of 1000, you got 200, right? Then xi is equal to x of 200 colon 201. Yi is equal to y of 200 colon 201. What that means? We are picking up the 200th records to 200th record x and corresponding y. Okay, and then we substituted xi and yi into the gradient formula. The formula did not change. Stochastic gradient descent or the original, batch gradient descent, we call that as original gradient descent. We call that as batch gradient descent. So the formula did not change. We substituted x's and the random theta and yi, and we got gradient. Okay, and then right we are calculating theta is equal to theta minus eta into gradient. That is calculating new theta. But between the green box and the theta, you have eta is equal to learning schedule of epoch star m plus I. So here, in the batch gradient descent, we have taken eta as a constant. Do you remember that? In batch gradient descent, eta was a constant. Do you remember?
Yes. 0.0002 something.
0002 in the equation, in the diagram, right, in the explanation slide, it was 0.0005, right? It was one constant. But here, learning schedule we are calculating the same eta we are calculating here. Okay, how are we calculating? Why are we calculating? I'll explain in a moment. Okay, so we are calculating eta and substituting that into the next theta formula and finding the theta and going back again. I'm in the second for loop only. Still I am in second for loop only. Only focus on second for loop. I'll go to the first for loop in a moment. Right? In the next iteration also, I calculated the total y cap. Okay. And then took the random, whatever, random index. Now you think that, we have got 250 or maybe 192 as the random index. So I have chosen xi 190 second record, yi 190 second records y, substituted into gradient. I've calculated, and then eta also I calculated, and then theta I calculated. Like this, right? I'm learning, right? I am learning theta with one record at a time. And now this for loop is over, right? There are m number of records, m number of times I chose random record and then calculated gradient and learned theta. So if I have 1000 records, 1000 iterations I'll complete, right? By the 1000th iteration, I'll get the predicted value and come out of that loop and calculate RMSE. Right? After 1000th iteration, I'll come out and calculate the RMSE, and I'm printing that. Okay. And going back to epochs, the first for loop. Okay. The first for loop is called as epochs. Right? EPOCH, epoch. And second for loop actually does, in our batch gradient descent, we are taking all 1000 records for each step. But in stochastic gradient descent, we are taking, in each epoch, we are doing 1000 iterations. Okay. So if I say 5 epochs, it's going to be 5,000 iterations. Okay. 5,000 single row manipulations. Okay. So the advantage here is we are not using whole data. Even if it is, 1 billion records, we can actually find out theta. So stochastic gradient descent picks a random instance in the training set at every step and computes the gradients based on only that single instance. So if I am actually afraid of switching back and forth between the screens because it is slow. So here, right, I came back to gradient descent screen again, and I'm showing you gradient descent, linear regression, gradient descent screen. So then once you are able to see that, let me know. Can you see now?
Yeah, yes.
Yeah.
Right now in this, right, this one step is made with one record. Instead of taking whole data, this one step is made with one record. Okay. The disadvantage is that, as Giri was pointing it out, right, if the record is having a altogether different pattern, the move may not happen in this direction. It may happen in the opposite direction. Actually, the theta should move slowly and reach to this place. But in some cases, what will happen is, because we are taking one record at a time, the move may not happen in the forward direction. It may happen in the backward direction. To control that, right? Suppose that I have taken a random record, it moved forward, and the next iteration, I took another random record, it moved backward. The same size. What happens? Will the theta stay the same place? Will the theta stay at the same place?
No.
No. What I'm saying is, first iteration it moved 1 inch forward. Second iteration it moved 1 inch backward. It will stay at the same place, right?
Yeah, it will not move towards the improvement.
Okay.
Towards improvement. You took random theta as 25. The first iteration it moved to 24 or maybe 26, right? And again in the second iteration, because of the data's, the records, individual records, right? So it is not, generalized. Individual records pattern it is trying to understand. So it may move backward. So in that case, right, what happens? It will stay at 25 only, or sometimes it may actually move even backward and it may go to 24 also, right? So to control that jump, right, first jump is big, second jump is small. What happens? Suppose that first step from 25 you went to 27. Okay. And the second step, if you are able to control the jump, even if it comes backward, right, it may come to 26 and stop there. Got it? Got it? No?
Yes, sir.
Yes, right? So first step, first step, 20 from 25 to 2 steps forward, 2 steps forward, and then second, even if it is going backward or forward, if you make it 1 step only, 1 inch only, what will happen? It will come back to 26. Sorry, 20. Sorry, 25 to 27. First step, 2 inches, and second step, either it goes forward or backward. If you are able to control it in such a way that it makes only 1 inch, what will happen? 25, no, 27 to, if it comes backward, right, it will come to 26. If it comes backward, if it goes forward, it will go to 28. So that way, right, you will be moving forward only. So to control that, what is the parameter we are using? What is the hyperparameter we are using? The step size.
Learning rate.
To control the step size, huh?
Learning rate.
Sorry,
Learning
learning rate, right? So that's what, yeah, that's what we are doing here. So if you look at the stochastic gradient descent green box, I came back to the green box again. You can see now, right?
No, sir.
No, Rama, not it.
Sorry, guys. No, this is painful. Because of my health, I was unable to come there. Now you can see,
Yeah, now I am able to see.
right? So the learning schedule is the method which is actually controlling that, If you look at this, right? So learning schedule, epoch star M we are doing, right? M will increase. With each iteration, M will increase. And with each epoch will also increase. In the first first epoch, the epoch may be 0, and maybe 0, 1, 2, 3, like that it will increase. Plus I, what we are doing? Sorry, M is a constant, so number of records. I will increase. So this number will increase with each iteration and each epoch. If you look at this learning schedule method, learning schedule function, T0 by T plus T1, right? T0 is a constant. If you look at the third line in the code, T0 is a constant and T1 is a constant. But T is the one which is increasing with each iteration and each epoch. If you increase the denominator, what will happen to the number? If you increase the denominator, what will have to happen to the number?
rate. The whole number will decrease.
Whole
Decrease.
number will decrease, right? So eta will decrease with each iteration and each epoch. Eta will decrease. Eta is nothing but the step size. So you are reducing the step size because you are using one record at a time, and the pattern may be different and it may jump around. Okay. Practically, we'll see how it is actually jumping. I actually took a data set and practically did it to see, for myself, how exactly it is jumping around. I'll show you in a moment. So stochastic gradient descent will jump around, and batch gradient descent will not jump around. It will be smooth, and it will be going, very, very smooth and sharp. But stochastic gradient descent will jump around, but still, the stochastic gradient descent is the best algorithm. I'll show it in a moment. I'll explain that. So far you are clear. So far you are clear. Why learning schedule is is calculated, and why sorry, why is it calculated like this way? Any questions there? Any questions?
Sir, what is the second statement, sir? An epoch equal to 5.
When epoch is equal to
5.
where and
Second statement from top.
that's a constant. I took epochs 5. See, in the batch gradient descent, what I did, iterations is equal to 70 I took, right?
Mm.
Like that here, epochs 5 I took.
Oh.
Okay. Got it?
Yes.
Same way for T0 and T1, 5 and 6 lakhs.
You can take any number there. You know,
Any
it's a
number.
constant. It's a constant. I know I actually took this code from Alan Geran's book, and that guy explained it very well. And when you look at the API, there will be these parameters in the API in the scikit-learn. No need to implement all this. I implemented it and I'm trying to show you because you need to understand each and every detail here. When you look at the, I'll show you the scikit-learn's API in a moment. You will have all these parameters there. Once you have the theoretical understanding, right, you will be able to understand those parameters well and use them well. Right?
Yeah.
So you have a bike, and bike is built by Honda. You're using it, but I am trying to open it up and show you, how exactly the mechanism is. That's how it is. Okay. Yeah. Go ahead. Any
So
questions?
in the second for loop, y predict equal to x dot dot theta. So there we are actually doing, calculating the complete on the complete data. Y predict is calculating on the complete data. So how is it efficient than the GD, gradient descent?
So here, okay, your question is right. We are actually, while calculating, maybe in this code, right? I did it this way, but you can put this y predict, right? Maybe after the for loop also, right? Let me take a pen and draw it and show you. I think so. The point here is while calculating gradient, I am not using whole data. That is one point, right? That point is clear. While calculating gradient, I am not using whole data. That is one good point, right?
Yeah.
That actually improves performance. You agree with that, right?
Yes.
The second statement, right? You made is also right. I should have kept that prediction outside, right? Prediction outside.
Even
That
though if
prediction
we
is
kept
not needed.
outside,
Sorry.
even though if we kept outside in this particular scenario, it will be calculated many
prediction
times.
will be calculating prediction is not a big calculation, right? So if we have 1 billion records, maybe you can take a batch of records and then do it. That's up to the situation, right? So this is just a simulation of that whole thing. And what you are saying is why this particular, I don't know whether you can see me drawing. Let me know when you see drawing there. Why this particular part here? This is actually using the whole data, right? I'm using that predicted value here to calculate RMSE, right? But in real time, right? In real time or in the implementation, the algorithm would have kept this particular statement here, right? Right. So instead of calculating in each iteration, maybe 5 times I am calculating this y predict and then trying to calculate the RMSE. That is one way. If you have 1 billion records, right? Maybe I took a sample, right? Here also, while calculating predicted values, I can take a sample. It is like test, right? Maybe 1,000 records I'll take as a sample and try to calculate this predicted value and then show RMSE on the test data, right? Got it? Got it?
Yeah.
So what you pointed out is right. This code, whatever the code I am showing you, stochastic gradient descent code, will not work if you take 1 billion records. That's for sure. Whatever you pointed out is for sure. But your implementation, when you are doing it with 1 billion records, you should be taking 1,000 record sample, random sample and then calculating RMSE and showing how exactly the model is working on random sample. Right? If it is working on random sample efficiently, it will work in production also. Right? Got it?
Yep.
Huh? Convinced, right?
Yeah.
Yeah. So the point is, you don't need to implement all this. This code I am showing you to show you how exactly the learning schedule is actually working, or how exactly we are controlling that. If you, I am drawing a parabola. Are you able to see?
Not yet, sir.
This is really. So right, in this stochastic gradient descent, I said that it's going to jump around, right? The theta you started here, it may go 2 steps forward, 3 steps backward, 2 steps forward, 3 steps, like that it may jump around. To control that jump, we have this eta. So we are actually controlling the theta. With each iteration, we are reducing the eta so that first iteration it will make big jump. Second iteration, even if it comes backward, right, the jump is going to be small. Right? Forward, backward. That way it will actually reach to the global minimum. Okay, that is one important thing we need to understand. Learning schedule, right? And then I forgot another point to explain. That's okay. To make the algorithm execute faster, as it has only one record to manipulate at each iteration. This makes okay. Algorithm can process huge training data since only one instance is taken. Okay. So the next point is the batch gradient descent actually finds out the best theta. And stochastic gradient descent algorithm actually, right? No, I am actually drawing one more parabola here. Okay. Stochastic gradient descent actually reaches the global minima and jumps around here. It actually jumps around, like that, like that, like that. So I said that stochastic gradient descent, is jumpy, right? It will actually jump around here only. It will not reach the global minima and stop there. It will actually jump around. But still, the algorithm gives you almost the accuracy as it was getting with the batch gradient descent. Batch gradient descent basically reaches the global minima and stops there. But stochastic gradient descent, right, it actually jumps around. So the difference in the thetas found by stochastic gradient descent and the batch gradient descent is going to be minute, right? If batch gradient descent found the theta as 25.6, right? The stochastic gradient descent will find theta as 25.601, right? Minute difference will be there between the batch gradient descents and stochastic gradient descents thetas. But still, the performance improvement we are getting with the stochastic gradient descent is very important. Or the amount of accuracy you are getting with batch gradient descent and the amount of memory you are spending, or the hardware resources you are spending, is not that important, or negligible. Whatever the amount of accuracy you are getting in the batch gradient descent is negligible when compared to the performance improvement you are getting in the stochastic gradient descent. Okay, and one more point is, if you execute stochastic gradient descent 100 times, right, you will get 100 different thetas, but those are all going to be very minutely different. First time you executed 26.601 you got. Second time you execute 25.6011 you will get. 25.60 0 you will get. 25.60 maybe 61 60110 or something like that you will get. And minutely different. It is actually jumping around here because it is jumping around here. Stochastic gradient descent, 100 times you execute, 100 different thetas you get. But algorithm, the performance is not going to change, or the model's accuracy is not going to change much because of this minute difference in theta. Equation, right? The minute difference in the theta, the predictions will not change much. Got it? Any questions there?
Sir, you did not show the exit point from this loop, so it will be at least some value of RMSE is the exit logic.
It is not, the. So you are talking about, I'll talk about that. It's called as early stopping. That what you are saying is, suppose that I took 5 epochs. No, correct me if my understanding is wrong. I took 5 epochs, but by third epoch, right, the algorithm reached here, and it is actually jumping around here only for 2 epochs. Can I come out after third epoch? That's what you're asking, right?
Correct, sir.
Yeah, that is called as early stopping. We can actually look at RMSE. If the error is not reducing anymore, right? You by third epoch you came to error like maybe 5 or maybe 10, and then the error is not reducing anymore. It is actually reducing maybe 0.001. So you put a condition saying that the previous error and current error difference is maybe 0.001, and for 10 iterations it is having the same difference, then you come out. That's called early stopping. Early, munduga aapet, right? Early stopping. Got it?
Yeah. So if you don't do early stopping, what will happen, sir? It will walk through all the records.
It will just run, and it will run and then jump around at the bottom itself.
Okay.
Nothing harm will happen because the slope is already close to 0. Theta will not get tampered much.
No.
It will not get tampered.
Go ahead, sir.
Yeah, please. I'm done.
What I'm not able to understand is how do we, because we are not checking any less than or greater than etc. in this logic. So
in this logic, I did not implement it.
Okay, fine. In the actual algorithm.
Orally, I'm explaining. Yeah.
Got it.
Actual algorithm will have it.
Got it, sir.
We call it as tolerance. The difference between the previous error and the current error is called as tolerance. If you set that, and how many iterations you want to look at it, also you set it in the algorithm. I'll show it in a moment, and then algorithm will handle it.
Okay, sir.
So any other questions on stochastic gradient descent? This is the algorithm we use in deep learning also. Mini batch we say, right? Instead of taking one record at a time, if you take random index, maybe 10 numbers, m comma 10, if you say, right, you will get 10 numbers there, 10 indexes. You take the 10 records, xis, ys, and calculate your gradient, then it's going to be more efficient. Then jump is going to reduce. If you take one record at a time, the jumpy nature will be too high. If you take 10 records at a time and try to calculate the gradient, the jumpy nature is going to be less. Right? Jump is going to be less and it's going to be more stable. That is called as mini batch gradient descent. Okay. So in deep learning, we use mini batch gradient descent. Okay. So let me move on, and then I'll stop for questions and discussion and all that. So this is the real important algorithm, right? I have tried to implement and show, right? I showed this already, right? The cost function. Can you see the stochastic? The next screen, on the right side I have a equation, and on the left side I have a blue box and whatever, right? The code.
Yes, sir.
Yeah. So on the right side, right, I actually showed you this yesterday itself. The cost function is y minus h of x whole square. Obviously there is 1 by m and sigma is equal to 20m. I just ignored it just to show you how exactly the gradient, the equation is actually matching. So this is y minus theta x whole square, and then I expanded it. That is the cost function, y square theta square x square 2y theta x, right? Now the gradient or slope is the derivative of this cost function. If you see, the gradient or slope is equal to, I use dou because in the derivatives in the calculus, right, d by dx is there and dou by dou x is there, right? So if you are doing dou, right, it is a partial derivative. If there are multiple variables and you need to do derivative with respect to each variable, then you do partial derivative. Right? In real time, you will have multiple multiple input parameters. So you'll have theta 1, theta 2, and so on, theta n. So you may have to do derivative with all those thetas. That's where I denoted it with dou. Right? So derivative of the cost function. So I expanded derivative of y square with theta, derivative of theta square x square with theta minus derivative of 2y theta x with theta. Right? Y square is a constant, right? With respect to theta is 0, and then uh, derivative of theta square with respect to theta is 2 theta, right? And x square is like multiplier, right? So even if there is other variable, right, it is like constant. It's not going to the derivative is not going to touch that. So x square minus 2yx, because d theta by d theta is 1. So I took 2x common, so it became theta x minus y. That's what is this, right? The blue box. Xi dot theta is the theta x minus y into 2x. Right? To multiply, to do the vectorized implementation, I transposed the x, because the m by n and n by p, you multiply, you get n by p matrix. Okay, and then whatever, the rest is all same. And epoch 1, epoch 2, if you look at this, right, how many calculations we are doing? If you look at it, 5 epochs, right? In each epoch, if I have 1000 records in the data, m is 1000. Suppose that m is 1000. How many calculations we did? Or how many iterations we did? 1000 m and 5 epochs. How many?
5,000.
5000 iterations, right? And then 5000 gradient calculations. Okay. In 5000 gradient calculations, we have got the best theta, right? If you see this, epoch 5, 3334 point whatever, 333 point whatever, right? Let us go back to the batch gradient descent. 334, okay. Yeah, batch gradient descent. Right, I am in batch gradient descent now. In this batch gradient descent, I have taken 70 iterations. Okay. And then in each iteration, how many matrix manipulation, how many records it is manipulating? 1000 records, right? While calculating gradients, 1000 records it is actually multiplying, or calculating whatever gradient for using 1000 records, right? So 70 into 1000, how many?
70,000.
70,000, right? You look at this, the epochs, by 70th epoch, you have got 333.62. In the stochastic gradient descent, 334. Right? One number difference, even one number difference. And if you take one more epoch, right, it will also get resolved. Right? In 6,000 to 7,000 calculations, you reach a place where batch gradient descent is reaching at with 70,000 calculations. In that perspective also, the stochastic gradient descent is better. Get it? Got it? Right? Number of calculations reduced with stochastic gradient descent. It looks like we are doing more iterations, but it is not. Even though we are doing iterations, but calculations are less. Right? It looks like 70 iterations only there, but actually we are doing 70,000 calculations. Here we are doing only 5,000 calculations. Got it?
So
Got it?
in batch stochastic gradient descent also, are we trying to calculate the y predict to calculate the RMSE?
Yeah, RMSE we are calculating, because I wanted to print it here. RMSE no need to calculate in each iteration. You can actually do 70 iterations, or maybe in between also you can do. Every 10 iterations you can do, or every 50 iterations you can do.
I mean, how will the algorithm calculate?
It depends on the implementation. So, scikit-learn guys will do it in different way. TensorFlow guys will do it in different way. I never looked into the code there.
Okay.
But in deep learning, right, you can make that choice. You know how after how many iterations you wanted to look at the error and see if model is working or not. You can make that decision. You can write it in that code, in your code. Did I answer your question, or did I get your question?
Yes, you got it and answered.
Yeah. Don't be worried about the error calculation. It is like to measure whether the model is moving in a right direction or not.
Yeah, but I'm just trying to understand
Complexity.
the internals. Yeah.
Yeah, complexity. Yes, good. So basically, right, if the with each iteration the error is raising, we should be decreasing the alpha, the learning rate. If it is not moving, as expected, right, then we need to increase the alpha, right? So we need to look at the error, but how frequently we want to look at depends on how much data we have and how much data we want to calculate. We want to use to calculate the error, right? If you have 1 billion records, you may not use 1 billion records there. Maybe 1,000 records you take randomly and then calculate the error and see how the model is moving. Got it?
Yep.
Yeah.
Sir,
This understand.
One question, sir. No, on the graphs, what you are showing, the y-axis is nothing but j theta. Is that correct, sir? The cost function.
Yes, sir.
Okay. So whatever this loop we are trying to iterate and find out, we actually try to find out the theta in each iteration, and in the end we need to keep calculating that cost function also. Yeah. And our objective is to get to a point where the cost function value is minimal and stays there. That's what is the objective of this all these
Yes,
the complete
sir.
algorithm. Okay.
Error is not reducing anymore. That's the point you actually, right? You spoke that same thing in a different language, different sentences. Error is not reducing anymore.
Yeah. Yes. Yeah, the reason is because we are discussing so many things, sir. At least sometimes I think we may get lost. That's why.
No, we will not. We will not, and we will not. No, why I'm saying we will not, because I'll show you a code example now, right? That will actually solidify most of it. And you need to work on one data set, maybe housing price data set, using stochastic gradient descent and play with it. Then you will remember it. Okay, that is one thing.
Sure.
And I'll take a pause, right? After, maybe in the for next 1 week also we'll discuss the same thing, because on the classification problem also we are going to use stochastic gradient descent classifier. There also it will actually, we'll talk about it more. Then I'll take a pause and explain the machine learning algorithm so that you will get some time to solidify this and maybe work with different data sets. And once we get into deep learning, right, again I'll come back to this in the sense we'll talk the same terminology. Okay.
Yeah.
So you will not forget.
Sir, I have a question regarding the RMSE formula. Actually, RMSE is nothing but like the square root of MSE, right?
Yes.
So MSE is nothing but like actual minus predicted by mean.
I think I did not do mean here. The formula wrong. The code was mistake. By M is not there.
Yeah.
Yeah, that's a mistake.
Okay.
That's a mistake in the code. I'll correct it. I'll correct it. That's not a big deal. Yeah.
Yeah. Okay. Well, I was going to say, okay.
That's a good point, actually. That's a good point. For future thing, right? This guy is saying RMSE and he should root squared error. It is root squared error, not the root mean squared error. That's a good point. I correct it. Yeah, M is anyway there, right? So I can use that M here. Yeah, I'll use that. Okay, good. Can I move on?
Yes.
Yeah. Now, right, how exactly the gradient descent algorithm is jumping around, we'll see. So I said that, the Gradient descent. Can you see how it works? Screen.
Yes, sir.
So the cost function theta and cost function, right? When you look at the graph, right, it is going to be jumpy like this. There will be bumps and all that like that, and whatever this low local minima global minima diagram, right? So like that it's going to be on a real data set. You see that an irregular cost function, right? It is actually jumping around, right? So sometimes what may happen is the algorithm may get stuck at the local minima. What is the slope at this pit? Do you see my cursor? What is the slope of the tangent at that pit?
0.
0, right? What happens to the formula? Theta is equal to theta minus alpha into 0. Theta is equal to theta minus alpha into 0. The theta may get stuck here. That is called as local minima. Local minima. These are all local minimas, and this is global minima. The bottom pit is the global minima. Actually, the algorithm is trying to reach to the global minima, but it may get stuck in between somewhere. Okay, but because of the jumpy nature of the stochastic gradient descent, it will jump out of the pit and somehow it reaches the global minima. Okay, that's another advantage, right? Because the jumpy nature's advantage is that one. Okay, so you got global minima, local minima concept. Any questions there? No, right? Let me show you on a real data set how the stochastic gradient descent is jumping around.
Yeah, how we know like whether the minima is local minima or global minima? So on the graph, yes, it is easy to understand.
Yeah. You look at the error and you are getting huge error, right? That means the algorithm stuck at you see, that's a good question. In real time, while working with the code, while working with the data, you look at error and try to assess. There are no graphs. You cannot do graphs because you'll have 100 features there and maybe 10,000 records. More features you cannot do graph. Only numbers you need to look into. The error, RMSE, MSE, or whatever, that R square score, whatever. If it is huge, that means the model may have stuck at some place there. Well, how do you know whether it's stuck or not? You change the hyperparameters. You change the learning rate a little bit and play with it. It is improving. That means previously it got stuck with. It's a trial and error. We call it as hyperparameter tuning. Very fancy word, but it's a trial and error. You need to play with the hyperparameters and see what's happening. Okay. So let me run this. Can you see the video here?
You're seeing small box. The video is not something coming up. Yeah, it came up.
Yeah. So the same data set, right? I used stochastic gradient descent and tried to. I did the graph, right? If you when you looked at this theta j theta graph on the batch gradient descent, right? The curve, the parabolic curve was so smooth, right? Very smooth, right? But if you see this, right? See, it is actually highs and lows, irregular cost function. So if you look at some points like these, right? My cursor is at some place. That's actually a deep pit. It may be looking very small here. If you magnify the diagram, right, it may be a deep pit and the algorithm may get stuck there because at that pit the slope of the tangent is going to be 0 and algorithm may find it difficult to come out of it. When you change the hyperparameters, right, the jumpy nature will change and it will anyway come out of it. Okay, so let me run this and show you. It may take some time for you to it's actually coming down. Theta is actually coming down, right? And if you look at the left side line, it is actually going backward and forward, backward and forward. Or if you look at the numbers, theta, right? Sometimes it is positive, sometimes it is negative. Sorry, gradient, slope. Right? It's going backward and forward, backward and forward. If you observe carefully, at the bottom of the pit, it is actually jumping a little bit, back and forth, back and forth. But it is not coming out of it. Right? It reached the global minima, and there it is actually jumping around, back and forth, back and forth. Right? Even if you see the line, it's actually moving back and forth, back and forth. Right? Stochastic gradient descent behavior, because of taking one record at a time, it does that. Maybe you are able to see that now, whatever I spoke. Are you able to see the jumpy nature?
Yes, sir. Yes.
Right? This is on real data. This is on real small data set. I have taken it and then took out all the diagrams and created this GIF. And I'm running this again, right? Observe the line, observe the dot on the, observe the line on the left hand side, observe the dot on the right hand side, observe this, observe the slope also down below. And theta also, right? Epoch 4, iteration 7, theta, right? Theta also changing, right? But in gradient descent, I'll run gradient descent again. It will not change, it will be strict. Once you are done with looking at gradient descent diagram, this graph, this video, right? Let me know. I'll run the gradient descent one again.
So when you say gradient descent, you mean batch gradient descent,
Batch
right?
gradient descent, yes. So are you done looking at this?
Yeah.
Yes.
Yes, sir.
Yes.
Hello? Can you hear me?
Yes.
Yes, sir.
Yes, sir. Yes.
So let me run that other thing. You'll see. Right, this gradient descent, it is going strict. It is not jumping around. Line will just go in the right direction. That's it. And stay at the best fit place. That's it. No, it's not going to jump around. Because of generalization, right? More data, more generalization. If you take batch gradient descent, right? You take more data in the batch, the batch size is big. The algorithm will be, jumpy nature will reduce. So these all concepts are useful in our, what you call it as. So that's it, for today. I am kind of tired. So tomorrow I'll take the class. More on the. I'll show you the code example and all that tomorrow. Okay. Okay, right?
Okay, sir.
So